bunch of stuff that happens since I started the lecture. It's on the board. So what we're doing is we're defining the things that we need to work with to define a manifold. And we're starting off from topological spaces, and I said that topological space is an open set. It's a set together with a family of subset of X that I call open set that satisfy the properties. An open set containing some element X, little x in X is called the neighborhood of X. This allows us to then define continuity of a function. Yes.
Should that be neighborhood of little x?
Sorry, yeah, neighborhood of little x. Thank you. Okay. So by now you're all familiar with the epsilon delta. Should be familiar with the epsilon delta definition of continuity of a function. I'm going to give you another definition, and I'm going to leave as an exercise for you to show that those two definitions are equivalent. The definition that you're already familiar with, and the one that we're going to be working with today. But intuitively, continuity of a function over a manifold is basically the statement that continuous functions map nearby points to nearby points. That's it. Okay. A function is continuous if it maps nearby points to nearby points. But I haven't told you about manifolds yet, so I'm going to have to define this in context of the topological set. So what do I mean by this? So more precisely, if X and Y are both topological spaces, and have some function that takes X to 1, then F is continuous if any open set U in Y, the inverse image F inverse U lies in X is also open. Okay. If any open set U Y, the inverse image of U is F inverse U X is also open. As an exercise, I'd like you to show that the function f that takes r to the n, r to the m, it's continuous according to this definition. If and only if for every x in R to the n and all epsilon greater than 0, find some delta greater than 0 such that the distance between vectors y and x in R to the n is less than delta means that the distance between f of x and f of y, standard norms on R to the n and R to the m, is less than epsilon. Okay, that's the standard epsilon delta definition of continuity. Now, nearby points, nearby points. I gave some definition that will work for general topological sets. If you specify to R to the n and R to the m, a function mapping R to the n to R to the m, then this definition collapses to the standard definition that you are already familiar with from real analysis. Okay. Just a fun calculation if you don't have anything else to do on Saturday. Okay. The utility of a manifold is that we can cover this space. Right. So it starts off with a topological space. We're going to equip it with a little bit more structure, and we can cover the space with patches that are all locally like R to the n. Right. Such a collection of open sets is called a cover of the topological space, and their union, like this here, is all of x. Okay, so basically I have some space. I can cover it locally with patches, and locally all these patches look like R to the n. I have to tell you about how we do these patches together, but locally I can cover them with patches that all look like R to the n, such that the union of all those patches is the full space. Right. And the key point here is that as long as I'm working locally within any patch, I can pretend I'm working on R to the n. So a collection of open sets is called a cover of the topological space X if the union of such sets is all of X. So I am of course waving my hand when I say I can pretend to work in R to the n, and I should make that more precise. So let's make that more precise. The way we come into this pretense is as follows. Suppose I have an open set X. That's my topological space. And inside X, I have some subset. So called U. Okay. From this subset, I can define a function that takes me between U and R to the n. Let's call that phi. So that's the picture. So given some topological space X and some open set U and X, we can define this function that takes us between U and R to the n. Such a function is called a chart, right? And it's a chart that allows us to pretend that we're working in R to the n as long as we stay within U. So a chart on X is a continuous function phi that takes us between U and R to the n. The key point here is that phi is a continuous function with a continuous inverse. So with a continuous inverse, denoted by phi inverse, and for U an open set. X. So as long as we stay within a particular chart, we can pretend using this as long as we stay within U, we can pretend that we are working in R to the n by using the chart phi. So let me give you an example. Suppose I have some function f that maps an open set U to R. If I have a chart on U, then I can turn the function f into a function on R to the n by composing it. So suppose f takes U to R. So here's U. Here's the real line R, and F maps U to the real line. Okay. The point is, since phi chart has a continuous inverse, I can turn this function, which maps U to R, onto a function that takes R to the n to R by composing it. First going from R to the n to U, and then from U to R. Okay. So in this case, F composed with phi inverse is a map from R to the n to R. Finally, I'm at the point where we can define an n-dimensional manifold. So an n-dimensional manifold, so M is a topological space that equipped with a family of charts phi, let's say alpha, that take us from open set U alpha to R to the n, such that what we call transition functions, I'll write those down just now, are smooth where they're defined. They overlap. Okay. So, and n-dimensional manifold M is a not one of those space with together with family of plots. Let's call them U alpha, sorry, phi alpha. And these phi alpha take the open sets U alpha to R to the n, such that the transition functions phi alpha opposed with phi, and let's say beta inverse, that take you between the open set U alpha and the open set U beta. Are smooth where they're defined. In other words, in their domain. One more definition that I can give you is that a collection of such plots phi alpha is called an atlas. So let's draw a picture of what this looks like. I've got my space. M. I've got open sets U alpha and U beta. R to the n, and I've got some map phi, it's chart, say phi alpha to R to the n, and I've got hash U beta, got another phi beta with inverse is phi beta inverse like such. And the composition where these two overlap, union in the intersection of U alpha and U beta, is the transition function that takes me between the open set U alpha and U beta. And it's defined through phi beta inverse, phi alpha. Okay. The definition that I've given has two important consequences. The first of these is that What it tells us is that if we patch together, or we can patch together the whole manifold from little bits, all of those little bits look locally like RTN. Okay. So every point X in this manifold M lives in some open, in some neighborhood, so some open set U alpha that locally looks like RTN. So every X in M lives in some open set U alpha that locally by locally looks like, I mean, I can find the chart when it comes to RTN. Second point here is that it allows for an unambiguous definition of smooth functions on M. Specifically, I have some function f that takes M to R, and I call that function smooth if the composition with phi alpha inverse, so this guy here that takes me from R to the N to R, which I understand how to define functions like this, is smooth. Okay, so a function f is called a smooth function on the manifold M if f equal to phi in the alpha that takes me between R to the N R X for every value of parameter alpha. The resulting manifold is called a smooth manifold because the transition functions, those that are up there, phi alpha and those phi beta inverse, is then a smooth function. Okay. So this is an important distinction to make between a manifold, smooth manifold, and a topological space. In the topological space, the transition functions are only required to be continuous, whereas we require these guys to be smooth. And we're trying to define a smooth function as infinitely differential. So require elements of C infinity. So we the manifold M is called a smooth manifold if the transition function okay, so this basically defines for us the set of objects that we're going to be working in, the spaces that we're going to be working in. There are a few more technical restrictions on the definition of manifold and mathematicians care about. Two in particular, what's called paracompactness and Hausdorff. The Hausdorff property and paracompactness are definitions that effectively eliminate particular pathologies with manifolds. Some of them we might encounter maybe a little later when we deal with manifolds that have singularities, singular points, but for the most part, we don't really care about those. If you want definitions of them, look up on Wikipedia, it's the answer definitions of what paracompactness and Hausdorff properties. But essentially, what we're going to be doing is calculus on these smooth spaces. So all I need are definitions that are given here. That are not what we need to do. Next time, 1 second. Okay. Good.
Can we define the transition functions to be smooth? So is there a distinction between manifold and smooth manifold then?
That's right. Good point. Okay.
So I think transition is so usually after living to state the we would have say
So at this level here, you're correct. I need them to be homeomorphic. Right? That's sufficient. But so I'm not going to be differentiating between smooth manifolds and manifolds. When we talk about manifolds, we'll almost always mean smooth manifolds. So next time I'm going to kind of go backwards a little bit to talk about vectors again. But now we're going to be talking about vector fields. So I want to introduce the idea of tangent spaces on these manifolds, and the objects that I define on the tangent spaces, and those objects are vector fields that live in the tangent space. And this is going to be necessary because then we're going to talk about how to compare vector fields in one that live in one tangent space, vector fields that live in a nearby tangent space. It doesn't define the idea of derivative.